Hi everyone. We still have a couple of transducers to talk about, and that's the PDA and the CCD. We already talked about the PMT. Remember I said that you never used an instrument that had a photodiode array, but we do have a really nice HPLC that has one. And if you used the ICP in lab, it had a charge couple device. And just a brief reminder, these transducers only work in the UV vis range. So let's talk about the PDA. The PDA, as you see here, is an array or collection of detectors. And some people call the PDA a DAD detector, which stands for Diode Array Detector. And I want to pull up that diagram of a grating monochromator to help us understand what a PDA is. If you think about it, we have white light striking this diffraction grating, and then upon diffraction, that white light is separated into the individual wavelengths. So if you think about it, couldn't we get rid of all of this and replace it with an array of detectors right here that can respond simultaneously to all these different wavelengths? That's what a photodiode array is, and this is its main advantage. It's responding to all of these different wavelengths at the same time. That makes it faster and a little bit more rugged because you don't have to rotate that grating anymore to change the wavelength. But a disadvantage could be that the resolution isn't as good. It just depends on how closely spaced the diodes are. If you go back to my diagram, notice how this diode right here is being struck by both green and purple radiation, which would suggest that this diode array is incapable of resolving green and purple. But again, that's just because of the way I've made my diagram. But that may be something to remember about the PDA. Resolution may not be as good depending on how closely spaced these diodes are. Let me show you the PDA in our Ultimate 3000 HPLC. That is the HPLC that has the PDA, but just a brief review. This is the pump on the HPLC. This is something that your HPLC didn't have. It was an auto sampler. It also has a column compartment. So inside of this compartment, that's where the column is. And right here, this is the PDA. So here I have a chromatogram from a former student. We're looking at signal as a function of time, and you can see that my student got signals for 5 different compounds. And that's great, but all we know is that we have a signal here. If you're using a PDA and you're able to measure more than one wavelength at a time, you can actually look at the absorbance spectra for all of your signals. And that's what I'm showing you here. You can get a lot more information about this peak that's labeled E. Again, you're able to measure all of these different wavelengths at once, allowing you to acquire an absorbance spectrum as each of your compounds elutes from the column. So that's the PDA. Let's talk about the charge couple device. If a PDA was a one-dimensional array of detectors, the charge couple device is a two-dimensional array of detectors, and each of those detectors is called a pixel. The main advantage is its sensitivity because it has such a low dark current, and the main disadvantage is that it's expensive. We do have a CCD in the ICP. Here's a diagram of our ICP. There's your plasma. Here you have white light being emitted by that plasma. This is the entrance slit to the monochromator. Here's that collimating mirror. This is your diffraction grating. The ICP also contains a prism. Notice our radiation has been separated, and all at once, all those different wavelengths strike that charge couple device, and you can see that our CCD has over 1 million pixels, and it's only the size of probably a square centimeter. So that's all for the PDA and the CCD. Hope you enjoyed the video, and thanks for listening.